would probably do on this problem is actually just combine these into n to the 3 halves, right? So rewrite that, that's 1 and that's a half, right? Add them together, so that's n to the 3 halves, right? So again, we're going to find the limit as n goes to infinity of absolute value of x to the n plus 1 over n plus 1 to the 3 halves, right? Times 3 to the n plus 1, and then times your reciprocal, right? So n to the 3 halves, 3 to the n over the absolute value of x to the n. Right? And so then as we start canceling, right, I've got one more x in the numerator here. So x to the n cancels. N plus 1 goes away and I'm down with the absolute value of x, right? Same thing is going to happen with the 3. 3 to the n is going to cancel out here. Right? And so then I'm left with this n to the 3 halves over n plus 1 to the 3 halves. Again, we've talked a lot about this. As n goes to infinity, yeah, it's going to be infinity over infinity. Okay, but they're the same infinities. They're the same rates. Right? So n to the 3 halves over n plus 1 to the 3 halves is simply going to go to 1. Right? If you want to, you can write it as n over n plus 1, all to the 3 halves, right? Like exponents, right? Kind of factor that exponent out. Okay, in here, right? Factor an n out of the denominator. 1 plus 1 over n. N's cancel, so it's 1 over 1 to the 3 halves. So it's 1 to the 3 halves, so it's 1. Right? There's lots of ways to justify that that's 1. Okay, but you need to know that that's just 1. I mean, we've been doing this for a while, right? And again, you should have known that's 1 from pre-calculus, right? Or maybe even an Algebra 2 class. So you should have kind of walked in with that idea of knowledge. All right, so when I do this, I'm left with the absolute value of x over 3, right? Right? Which again, we talked about from the ratio standpoint, right? We're never going to do a ratio test on a polynomial, right? Or on a power, because you're going to get 1, right? So that's why this portion is producing a 1. Okay? If I didn't have the rest of these, ratio test would be inconclusive and wouldn't do me any good. Okay? But you can definitely go straight from here and say it's the absolute value of x over 3. You don't need this for this problem, for this type of problem. You don't need to justify that. I mean, you should know that that's going to go to 1 to get this. That's just fine. Yeah.
So on the test, how are we supposed to know when to use L'Hopital's, when say it's indeterminate, when there's infinity over infinity, and when we're just supposed to say it's goes to 1?
Yeah, well, I mean, embedded in this type of problem for this purpose, right? So this isn't a problem that's starting off with find the limit, or, you know, it's not what the premise of the problem is, right? The premise of this problem is to find an interval of convergence, right? So kind of along the way, you need to use it maybe in there, so they're just okay at this point in time. But if the problem simply said, you know, find the limit, like this was the problem, it was just find the limit as n goes to infinity of n plus 1 over n or something like that, right? Either L'Hopital's it or factor an n out, or, you know, do something to justify that's what it is. Because then that's the purpose of the problem, right? The purpose of the problem is to see if you can evaluate limits, right? What skill am I testing you on? Your ability to evaluate limits that are of an indeterminate form.
Okay.
That's not the skill we're testing on here,
This is
right?
serious.
It's right. It's different purpose. We just need that skill to execute the problem. And again, at this point, you've already gone through all of that. So I mean, you should just, I mean, that should be second nature. So they're kind of like, all right, just go through it. Quickly do it. All right, so this is going to converge when this is less than 1, right? So it converges when the absolute value of x is less than 3. Again, 3 is your what? It's my radius of convergence, right? Okay, so again, if the question asked you for the radius of convergence, you would say capital R equals 3, right? Or my radius of convergence equals 3, okay? You'd be done then, okay? Where is it centered at? 0, right? Centered at 0, right? No x minus or x plus right in the parenthesis, right? So it's x minus 0. Okay, so then I know my interval is from -3 to 3. Right? Non-inclusive, never inclusive, right? To start with. Okay, because again, the ratio test is inconclusive when L equals 1. Right? So I have no clue what's going on at -3 and 3. I know it converges absolutely, right? We put the absolute values on it, right? I know it converges absolutely between -3 and 3. I know it diverges greater than 3 and less than 3, but what I don't know is what it does at 3 and -3. Because again, the ratio test says that would be when it's equal to 1, which is inconclusive. All right, so now we got to go back in to our series and replace x with both 3 and -3, right? And just analyze that whole new series, right? Figure out what does that series do. All right? All right, so we got to figure out what do I change on my endpoints. Do I leave them non-inclusive? Do I change them to inclusive? Do I change one of them to inclusive and one of them to not? Okay. All right, so let's test x equals 3 first. Doesn't matter which one you do, but I typically like to test the positive one first. Gives me just a better sense of what's happening with the series and kind of helps me make some conclusion about the other one as well. All right, so I get the series n equals 1 to infinity of 3 to the n over n to the 3 halves times 3 to the n. All right, again, I'm just rewriting that n root n is n to the 3 halves, which is going to be really important. All right, it's going to be helpful when I see it that way anyway. So what happens? 3 to the n's cancel. So I'm really looking at the series 1 over n to the 3 halves. Which, what? What does it do? Converges because no such thing ever that it converges because it goes to 0. There's no such thing as that, right? It diverges if it doesn't go to 0. But there's no such thing. You can never ever say, right? You've got to write that down somewhere. I can never ever say that a series converges because it goes to 0. There is no such thing as that. It's not something in your vocab. All right? It's not a test. There is no converges because the terms go to 0 test. All right? Why do we know this converges? P's greater than 1. Right? It's a P series, right? P's greater than 1. This is going to converge. Right? How could I test that? I could integral test it, right? I don't need to, right? But again, if I went back and wrote this as 1 over x cubed, right, and integrated it, the x would stay in the denominator. Right? Because when you add 1 to -3 halves, you stay negative, right? Which means the x stays in the denominator, which means as you go to infinity, that portion is going to go to 0, right? So you're going to get a finite number, right? But this converges, right? Because P is greater than 1, right? And again, it converges absolutely, right? This is all positive terms, right? So when this is all positive terms, it converges. So at 3, we're a little equal to, right? Okay, so now we know it converges absolutely from -3 to +3 and inclusive at the +3. Okay, so now we got to check -3. As we talked a lot the other day, I kind of have a feeling about what I should get as a series here. I should get the same one except for it alternates, right? So I'm going to get -3 to the n over n to the 3 halves and 3 to the n, right? Which leaves me with -1 to the n, 3 to the n to the 3 halves, and 3 to the n. Again, the series. So the 3 to the n's cancel. So I get the exact same series I got when x was +3, except for that it alternates. All right? Again, First thing I want to do with this series is find out if it converges absolutely. Which means I want to make all the terms positive, which means I want to ignore the negative 1 to the n. And what series do I get? Same one as before, right? Which we figured out converges. Okay? So then I'm going to come back here and put an inclusive on that. Yep, so again, the idea is when we ignored the alternating, right, we made all the terms positive. What did that series do? Same thing as the one up here, which did what? Okay, so that means this series converges if all the terms are positive. Right? Okay, but again, you got to understand the premise of this. If every single term is positive and I add them all up and it converges, that means they sum to a finite number. So if one term is positive and the next term is negative and then positive and negative, aren't they guaranteed to sum to a finite number as well? Has to. Again, the largest the series will ever get is adding up all positive numbers. Right? If every single number is positive and I add them up, the series just gets larger and larger and larger and larger and larger, right? The sum of the series gets bigger and bigger. But if that sums to a finite number, then when the terms alternate in sign, that also has to sum to a finite number. Has to. There's no possible way for it not. Okay? So if the series converges absolutely, then that series must converge, right? So that's what we figured out here, is that this series, when x equals -3, converged absolutely because it became this series up here, right? Okay, so since this series converges absolutely, then this series must also converge. Right? So if a series converges absolutely, meaning if all the terms are positive and that series converges, then the series you're talking about must also converge. Whether it alternates, whether it doesn't alternate, whether all the terms are negative, whether the first 27 are positive and then the next 28 are negative and then whatever. Who knows? It doesn't matter. It doesn't matter what the sign of any of the terms are. Okay, if it converges absolutely, then the series converges. Okay. Right, so again, that's why you're testing for absolute convergence first, because it's a big, powerful test. Okay. So if all the terms are positive and they sum to a finite number, then when some are and some aren't, also it's got to sum to a finite number. Okay. All right. Now, let's go back to the same problem. Let's change something. Let's get rid of the n and just have it be the square root of n. All right? So if it's just the square root of n, does anything change from your initial work? No. You'd have an n plus 1 to the 1/2 and an n to the 1/2. Ratio test is going to do the exact same thing, right? The n to the 3/2 and n plus 1 to the 3/2 went to 1. N to the 1/2 and n plus 1 to the 1/2 is going to go to 1, right? So that doesn't change. Okay? Now, when we test our endpoint, so we're still -3 to 3. Okay, but when we test 3, this doesn't become 1 over n to the 3/2, it becomes 1 over n to the 1/2. And what does that series do? Diverges, right? Because p is less than 1. Okay? So then, right, so I came up here. I was looking for this. Let's get rid of this for a second. Okay. And so now I'd have my -3 to 3, right? And I just figured out at 3 it diverges, right? So I'm not going to put a equal to symbol on it. Alright? But now let's check -3. When we check -3, we should get the series -1 to the n over n to the 1/2. Okay? Which again, when I test it for absolute convergence, would be the series 1 over n to the 1/2, which diverges, okay? But there's a chance this one still converges, okay? I didn't prove that this one diverged. I proved that its absolute value diverged, right? I proved that when all the terms were positive, the series diverged, okay? But there's still a chance for this series to converge using what's called an alternating series test, okay? An alternating series test basically has 3 things you have to prove.
So,
Yep.
why did we do that for the original equation? Why did we? Oh, because you converge.
Because it converged absolutely.
Yeah. Okay.
Right? So again, that tells me that it converges well, no matter whether the terms alternate, whether they're all positive, all negative, all half negative, half positive, not in any order.
Okay.
Again, that's why we do an absolute convergence, because it's powerful and it tells me no matter what that's, again, take those numbers converge.
Okay.
No matter what happens, no matter what their signs are, no matter what's going on with them. Okay? So here's the big idea with that, though. I'm not going to this series test until it did not converge absolutely. Right? This is a tertiary test. Right? I don't come to this test until I tried absolute convergence and failed. Right? Okay, so I'm not coming to even try this. I don't go to this right away, right? And that brings up, right, Elizabeth was bringing up, I'm not going to this test first. Okay, yeah, that series alternated a minute ago, but I didn't do the alternating series test on it, right? Because again, it's a secondary test. I'm only using it if, when I tested for absolute convergence, it diverged. Okay, so I'm coming to this test second. Okay, all right, 3 things that have to happen. Terms must decrease. So got to get smaller. Makes sense. We've been talking about that all along, right? So terms got to get smaller. Terms must go to 0. In theory, we should already have tested this, right? Should have done the nth term test on it anyway, right away, okay? But sometimes, you know, either you forget that or the problem just kind of looks kind of challenging, right, from the get-go. So you're like, I'm not really sure I want to take my time to try to find, you know, what happens as n goes to infinity. So you kind of just skip that test and went into, you know, something else, okay? But basically, again, if the terms don't go to 0, we would have already kicked it out and said it diverged right away by the nth term test, right? Which means we never really actually gotten to this point in time anyway, okay? And the last thing, and this one's going to sound a little bit weird, but the terms must all be positive. Okay? Now, when we're talking about the terms, we're talking about a sub n. Okay? Which means we're ignoring what part of the series? The -1 to the n, right? And so if I ignore that, and I just look at the a sub n, if those are all positive, what is the actual series going to do? Alternate, right? So basically all this is saying is that it better be an alternating series, right? It's just sort of a weirded, you know, worded weirdly and kind of what it means. But basically if you ignore the -1 to the n, and all the terms are positive, then the -1 to the n will make the terms, the actual terms of the series, alternate. Okay? So these are my premises, right? So number 1, basically a sub n plus 1 has got to be less than a sub n, right? Terms have got to get smaller. All right. Premise 2 basically says the limit as n goes to infinity, right, of a sub n better equal 0. Right, and then premise 3 is that it has to alternate. Okay? And so if these three things are all true, terms get smaller, terms go to 0, and the series alternates, then the series converges conditionally. By the alternating series test. Okay? So the alternate series test only tests for conditional convergence. Basically saying this series only converges on these conditions. Right? That the only reason this series converges is because it alternates. That if this series didn't alternate, it would diverge. Right? That's what this test is saying, is that the only reason this series converges is because it alternates. If it didn't alternate, it would diverge. Okay? Okay, so the difference between these two problems we looked at is that 1 over n to the 3 halves, right, converges absolutely. That series converges whether or not the